So for the next hour, what I want to do is perhaps talk about something different. My lab does not work on quantum computing. My lab works on nano and micro devices. Now, for a long time, micro and nano technology has always been a science. So what I'm going to talk about today is really to convince you, perhaps, it is no longer a science, but more of engineering. So I'm going to talk about some of our work, which is really close to commercialization. So I am not going to talk about mathematical equations. I believe we have seen a lot of those for the past few days. I'm not going to talk about science, but what I'm going to talk about is really the engineering and how to engineer nanomaterials into biomedical instruments that we could use in a hospital. So this is an outline of what to expect for the next 40 minutes. I'm going to talk about diagnostic and therapeutic instruments. In my lab, we are actually focused on different imaging modality, specifically X-ray CT machine. The second topic I'm going to talk about is microelectromechanical systems, or MEMS technology. We are using that technology for ultrasound imaging applications. The third topic I'm going to talk about is also related to imaging modality. In this case, I would be talking about optical imaging modality, particularly OCT. Now, the last slide, I'm going to give you some of my view of what I think would be the next generation of imaging instrument that integrate both micro and nano technology. So before I start, I'm just going to talk about my university and as related to your quantum and nano center here in Agra. So University of Waterloo just opened a quantum nanotechnology center. It was just 2 months ago. We have Stephen Hawkin, who actually helped us open the center. The center is an investment of $160 million. So this $160 million facility would house fabrication facility. Within the fabrication facility, we would have metrology, we would have nanobiosystem, all housed within the same center. Now, within the same center, we are looking at putting over 50 nano and quantum researcher within the same building. So this is, I would say, one of the largest initiatives in quantum nano anywhere on this planet. So, and I do welcome any of you who are around the vicinity of Waterloo to please come by and give us a visit. Now, in my very first slide, I did talk about the different modalities. My lab, one of my research directions is really to couple different imaging modality for both therapeutic and diagnostic application. Now, this slide here actually shows all the imaging modality that we are currently using in a hospital. So on one hand, we have MR imaging, we have ultrasound imaging. In the center portion, which is really, this is the entire spectrum of wavelength that we're currently used to image human tissues. In the mid-wavelength region, we have the optical imaging modality. On the far end, we have the X-ray. Now, from ultrasound to optical to X-rays, we could both use it for either therapeutic or diagnostic applications. Now, obviously, why do we need such a wide spectrum of imaging modality? Well, for a physician to actually interrogate a tissue, he or she require different information. Now, all these imaging modalities give physician different information to work with. So in my lab, what we're trying to do is to integrate all the modality within the single instrument. So by using one single instrument, the physician would have the capability to perform ultrasound in collaboration with X-rays or imaging. Or if you can imagine, we could use ultrasound imaging, optical imaging, but at the same time use X-ray for therapeutic applications. X-ray in this way will be applied to kill cancerous tissue. So if we were to have that kind of capability, it would increase or it would better the quality of life for cancer patients. Now, first off, I'm going to talk about X-rays. Now, this X-ray picture here was taken in 1895. Now, this is arguably one of the most famous X-ray pictures that has been taken. Now, in order to take this X-rays, well, obviously we need an X-ray tube to generate X-ray. This particular picture was taken by a Crookes X-ray tube. Now, it was invented back in 1895, a little over 100 years ago. Now, if one go to the hospital to look at X-ray diagnostic instrument, the way we generate X-ray has not really changed too much for the past 100 years. The detection technology has improved with the advent of CMOS technology and integrated technology. But in terms of the X-ray generation, it has not changed much for the past 100 years. Now, I'm going to talk about why has it been a challenge to replace the current X-ray generation technology. Now, X-ray has been used in many different applications, not just biomedical. But I'm going to use biomedical application as an example. Within biomedical application of X-rays, we have conventional chest X-rays, we have dental X-rays, we have CT scanner. So I'm not too sure how many people has done a CT scan before. A CT machine actually uses X-ray to image the body in 3D. So what it does is it has a couch. The patient will be lying on this couch. The patient would be slowly moved within this circular machine here. So that would provide one axis of scanning in this direction. Now, the other two axes of scanning is provided by the X-ray itself. Now, within this circular machine here, you have one single X-ray generator that is sitting on a mechanical gantry. And it would be moved around the patient in a 360-degree format to create multiple 2D images from many different angles. And I will talk about why is this such a problem. That is the diagnostic application of X-rays. We also use X-rays for therapeutic applications. Now, this is an example of an image-guided radiation therapy. In this case, we are not concerned with imaging, but rather we are trying to generate high-energy photons to kill tissues, particularly cancerous tissues. So the patient, again, will be sitting on this couch. He or she will be irradiated by high-energy photon beam to kill tumor within the body. A later technology would be something we call an electronic brachytherapy. Now, we all know that cancerous tissue or tumors are within the body. But we are generating photons from outside the body that goes into the body to kill the tissue. Now, we all know that photons has no eyes. It would have to penetrate healthy tissue before it can actually reach the cancerous tissue. So on the way to that tumor, the photon will be killing off healthy tissue as well as the cancerous tissue. So in order to counteract that or to minimize the lateral damage to healthy tissues, we have the electronic brachytherapy. And that would really require a surgeon cutting people up, opening people to expose the tumor or the cancerous tissue, to insert the tiny X-ray into the patient, to irradiate the patient right on spot. Now, I'm going to talk about the technology we have developed in our lab and a few labs across the globe that really focus on miniaturization of X-ray tube, not only to facilitate multiple and array of X-rays around the patient to achieve CT scanning, but particularly if we can insert this X-ray machine within an endoscope or a catheter. So without any open surgery application, we can insert this into human cavity to perform radiation therapy applications. Now, the reason, as you saw, all the X-ray machines were really big. Now, X-ray machines are really big and bulky is because of the way we generate X-rays. Now, besides being big and bulky, there are other disadvantages of the conventional way of generating X-rays, which is the current X-ray machine has really big power consumption. And the reason being, to generate X-rays, this is really, I'm not going to give a lecture on how to generate X-ray, but this is what happened in a nutshell. What we need is access to free-flowing electrons. To generate free-flowing electrons, we need to heat up metal filament. So this is a metal filament. We heat it up to about 1500 degrees Celsius, at which point electron will be spontaneously emitted from this metal filament. It is just a matter of imparting kinetic energy to those free-flowing electrons, so it flies through free space. On the opposing end of the cathode, the anode is a heavy metal material. So when you have a high energy photon hitting a heavy metal, what it do is it generates X-rays and it generates excess heat. In fact, 99% of the energy manifests itself as heat. Only 1% is shown as X-ray. So it is not a terribly effective way of generating X-ray, but this has not changed for the past 100 years. Now, besides big and bulky, besides the high power consumption because we have to heat up the metal filament, it also have really slow response because we need to heat up the metal filament. If we want to shut off the X-ray, we need to cool it down. If we want to turn the X-ray back on, we need to heat up the metal filament again. So it really depends on the thermal conductivity of the metal filament, which really governs the time response of the X-ray machine. These are the disadvantages facing us today, but again, we have no clear direction on what to do with this, at least until 5-6 years ago. Now, I did say that in order to generate X-rays, we need access to free-flowing electrons. So if we were to have a material that could generate electrons, not by thermiotic emission, but by field emission, then we could take away the metal filament and replace that with this magic material. Now, it turns out that carbon nanotube is such a material. So what we want to do is to replace the metal filament with an array of carbon nanotubes. Now, carbon nanotubes are amazing nanomaterial that shows that it could emit electron when it's subjected to electric field. So if you put a single strand of electron within the capacitor, each strand of carbon nanotube would act as electron guns. It would shoot out electrons. Now, the amount of current that one could extract from a single strand of carbon nanotube is actually quite small. But then we could grow billions upon billions of arrays of carbon nanotubes. So collectively, when you have billions of carbon nanotube emitting electrons at the same time, we could increase the current flow. Now, if we are able to do that, then we could potentially do quite a lot of things. We could generate X-rays at room temperature, as low power, and at the same time, it would have really fast response because there's no heating involved. There's only electronically controlled electric field. Now, if we are able to do that for a single pixel of X-ray generator, then one could imagine we could generate an array of X-ray generators. So these are single strands of carbon nanotube. You can see here this is actually a 2D array of single strands of carbon nanotubes. that we have fabricated. Now, the key here is by miniaturizing the X-ray machine, then we could put it at the tip of an endoscope, so it could be inserted into human cavity to generate X-ray from inside the body rather than from outside. Now, I'm going to talk a little bit about field emission. If we look at any conducting material has the capability of field emitting. And that means that we could actually extract electron from a conducting surface, provided that we give it certain criteria. Now, in order to extract the electron from a conducting material such as metal, we really want to have the electron jump from the Fermi level to the vacuum level. Now, at 0 Kelvin, all the electron is sitting beneath the Fermi level. And if it were to jump over the work function to the vacuum, it would be quite hard because we need to impart a lot of energy into this material in order to extract the electron from it. But luckily, we have ways to make it simpler. If this conducting material is subjected to electric field, we could actually distort the vacuum level. Now, the vacuum level could be distorted in the form of this green line. Now, obviously, the red line is governed by the electric field. Now, if the electric field is large, the greater the deformation of the green line. So in this case, electron does not need energy to overcome the work function of this material, but rather it only needs to tunnel through from the Fermi level across the green line into the vacuum level. Now, from this graph, you could tell that if the electric field is really big, it would be a lot easier to extract electron from this metal. You could also deduce from this graph, if the work function is really small, it would also be relatively easy to extract electron from this material. So first, if we want to choose a material for field emission application, we want to choose something that has really small work function. At the same time, we want to choose a material that has really high aspect ratio. Because if we have a really high aspect ratio structure within a capacitor, then the really high aspect ratio structure would really act as a lightning rod. So for a given electric field, we would have a really high concentration of electric field at the tip of the conductor. Now, given that we have really high electric field at the tip, and we have really low work function, we have the capability to extract a lot of electrons. And carbon nanotube happen to be that material. Now, I am not suggesting that carbon nanotube has the lowest work function, but it has one of the highest aspect ratio one could actually grow from a substrate. Now, to compare the difference between a hot cathode and a cold cathode, which is comparing between thermiotic emission and field emission, the main advantage of field emission is we could extract high current density because we could fabricate an array, a high density of carbon nanotube. We would have fast response because there's no heating and cooling involved, and we have the capability of generating multiple X-ray arrays. Now, the potential applications of what we're trying to do is to have multiple X-ray generator that is pulsed with a certain delay so we can image an object from different angle. Now, this concept is very different from the conventional CT machine that you just saw. Because in the conventional CT machine, we only have one X-ray generator that is moved around the patient on a mechanical gantry. Now, what we are suggesting here is if we could miniaturize the X-ray generator, then on a plane, we could have multiple X-ray generator. So what we are proposing is a solid-state CT machine without any mechanical gantry at all. It would obviously have many advantages. That would include fast responding scanning time around the patient. If we are able to scan the patient in a really fast manner, then we could actually produce a really good quality image, because we could decrease the amount of motion artifact caused by the patient within the image. So that's one advantage. The other advantage is making really small X-ray emitter allow us to insert this within a catheter. So a catheter could be inserted into human cavity to generate therapeutic X-ray for cancer treatment applications. Now, we have looked at many different structures of doing this. We have looked at metal spin emitter structure. This is a single emitter with the gate structure to generate electric field, such that each spin emitter would generate electrons. The advantage of a spin emitter is it has a polysilicon underneath. Now, the polysilicon acts as a ballast resistor. And I'm going to talk about the advantage of ballast resistor underneath the emitter. Now, that's one architecture that we have looked at. The second material we have looked at is CNT thin film emitter. We have looked at sparsely distributed vertical carbon nanotubes as thin film emitter. We have looked at randomly aligned emitters for field emitting. We have looked at densely populated vertically aligned carbon nanotube for emitters. We have also looked at just random distribution of vertically aligned emitters. So the reason that we have looked at different morphology of CNT as well as different architecture is really to increase the lifetime as well as the current stability. Now, in the end, we have came up with a new structure, which is a hybrid structure of the CNT field emitter and the spin emitter architecture. Now, the story obviously does not end here. So what is the problem of using CNT as emitter? Well, CNT has the capability of emitting electrons, but it would burn like candle as it emits electrons. So as carbon nanotube burns as candle, it would obviously limit the lifetime of the emitter. That's one problem that we have to solve. The other problem is if we were to have a randomly aligned carbon nanotube, as one CNT burns off, the length is decreased by the electrostatic force interaction. A new CNT would pop up to replace it. And as this CNT burns off, new CNT would come into life and start emitting. Now, this would increase the lifetime of the emitter, obviously, because new CNT are always popping up to emit current. But the problem we face is instability in current, as you can see here. This is a fluorescence experiment of an array of CNT. You see hot spots of current emitting CNTs, and you see cold spots as well. So what you're looking at here is certain CNT are taller than the other CNT. Because it's taller, it has a really high concentration of electric field. So this single strand of carbon nanotube emits more current. As this CNT burns off, you have new CNT, which is taller, and it start emitting current. So we are talking about non-uniformity of current intensity. We are also talking about non-uniformity of current emission across a 2D area. So these are the technical challenges that we have to address. So I did talk about the ballast resistor, and it was first designed for the spin cathode that you just saw. Now, in order to solve the current instability problem, we thought of integrating the ballast resistor underneath the CNT. Now, we want to be convinced that this can actually improve not only the uniformity of current intensity, but also the uniformity of current distribution across a 2D space. So we have done a lot of simulation on this. So we have worked under the assumption that if a CNT array has a 6% difference in height, plus minus 6% difference in height, it has a plus minus 4% in diameter. So given this really small difference in height of the CNT, as well as the diameter of the CNT, we want to know how much of that it would influence the current that we can extract from this 2D array of CNT. It turns out that it could be as much as 20%. So even the height difference and the diameter difference is less than 6%. The current that we can generate could fluctuate as much as 20%. Now, if one look at the fabrication process of CNT, 6% difference in height is actually pretty good. But even given a very good fabrication process, we still have to tackle the problem of huge non-uniformity in current extraction. Now, this is particularly important for X-ray generation, is because if the current is not stable, then the photon generation is not stable, and hence the image quality cannot be guaranteed. This is from the diagnostic perspective. From the therapeutic perspective, is we want to guarantee the number of photons that we're using to irradiate a cancer patient. If the number of photons is fluctuating by more than 20%, then we have a huge problem. So at this point, we are convinced that even with a good fabrication process, we are still not able to address the problem of current non-uniformity. So we have decided to, before growing the CNT, is to grow a layer of polysilicon to act as ballast layer, ballast resistor layer. So this is a simulation of, given that we, on this resistor layer, we have from 0 ohms to 100 ohms. You could see that the emission current is effectively suppressed as we increase the resistance of the ballast resistor. Now, one could obviously say you have solved the non-uniformity problem, but now you are extracting less current. Now, but we can obviously increase the electric field to increase the current level, but at the same time, maintain the uniformity of the current extraction. So at this point, at least from a theoretical point of view, we are convinced that by incorporating a resistor underneath an array of carbon nanotube could potentially solve our problem. Now, this is what we have done in the lab. This is a spin emitter. This is a single strand of CNT. This is a hybrid structure we have came out with on a substrate because another engineering challenge that we have to come up with is we are trying to allow CNT to act like a spin emitter. And the challenge is, for a spin emitter, it is a solid structure with a really broad base. So this broad base has a really tight connection with the bottom substrate. But with the CNT, because it's a really thin hollow tube, so the contact between the CNT and the substrate is really minimum. It is actually very easy to pull off the CNT from the substrate. Now, this is an engineering challenge that we have to overcome. Now, through many experiments, we have actually, it's actually more trial and error that we have done this so many times that we have come across this new architecture where on the bottom electrode, we deposit a contact pad that has really good adhesion to CNT. So in this point, we can guarantee the uniformity of the current, but at the same time, we guarantee the mechanical integrity of the CNT strand. So we have fabricated this array of CNT. I'm not going to talk about the fabrication process in detail, but we have gone through e-beam lithography. We have patent CNT catalysts. On here, we have deposited the ballast resistor level layer. We have grown the CNT. Now the CNT is sitting on a resistor pad, and the resistor pad has really good adhesion to the ballast resistor layer. Now at this point, we are ready to perform some experiments. This is very new work that you're seeing here. This is a X-ray machine. This is a benchtop size. It's not optimized right now. This is a single pixel of CNT array. So this is a single X-ray generator. We have also fabricated a 3x3 CT machine. So on here, each dark spot is actually a single X-ray generator. So on this chip here, which is no bigger than a single quarter, we have a 3x3 CT machine. So essentially what we could do here is on a quarter-sized coin, we are able to image a large area of the patient. Now, if you can imagine, if we have many of these coins positioned around the patient, then we could electronically scan the patient from left to right without any mechanical motion at all. Now, this is the X-ray generation that we have performed with our CNT arrays. We have not done therapeutic X-ray yet. This is in the kilovolt range, so it's more for a diagnostic application. As we have it running as much as 27 or close to 30 kilovolt. And you could see instability here. The instability is caused by the outgassing of carbon nanotube. So at this point, carbon nanotube is still burning off. As it burns off, it's releasing carbon material into the vacuum chamber, and that would, degrade the quality of the X-ray. But we're confident that at the level of 25 kilovolt, we can create a really stable X-rays. And we have done imaging of our X-ray machine. So this is a integrated circuit, package integrated circuit. Through our X-ray tube, we have imaged what's inside this integrated circuit. So each electrode here is on the order of 100 microns. So using our X-ray machine, we are, at this point, without any focusing at all, just emitting electrons, converting it to photon, and imaging applications, we are able to achieve around 100 micron of resolution. So I'm going to stop with the X-ray machine and move on to ultrasound. So I'll come back to the X-ray at a later stage. So I know everyone knows what ultrasound is. I believe most people has done ultrasound imaging before. Now, I'm not going to talk about the basic definition of ultrasound, but I would say this. For clinical ultrasound, it is typically around 1 to 60 megahertz. For ultrasound, the higher the frequency, the less the penetration depth. The lower the frequency, the deeper the penetration depth. But high frequency gives us higher resolution. If we want to image really small structure within tissues, we need to move on to higher frequency, although we are compromising on the penetration depth. Now, if we want to move beyond the 60 megahertz regime, the current way of generating ultrasound does not meet that requirement. So in the future, if we are looking at sub-micron structures within tissue with ultrasound, it simply cannot be achieved by the conventional way of generating ultrasound. Now, the conventional way of ultrasound is this. We have a piezoelectric material. We apply voltage to this material. This material would obviously deform. We take away that voltage. This material would move back to its original shape. So by applying voltage and taking away voltage, what we are trying to do is really making the piezoelectric material vibrate. Now, the speed of the vibration would determine the frequency of ultrasound we can generate from that piezoelectric material. So if we can generate really high frequency from this small crystal, now, how do we change the frequency? Well, we need to cut the crystal down to really small size. Because small crystal would have high resonant frequency, big crystal would have low resonant frequency. Now, at the level of 60 megahertz, we have to cut the crystal down to around micron dimensions. And each one of these conventional piezoelectric transducer is manually cut. There is no way to automate this. So if one goes to the hospital to perform ultrasound imaging, if you break apart that machine and look at that piezoelectric transducer, that was cut manually. So we have all experienced a single ultrasound transducer. The technician would move around your body to achieve the mechanical scanning applications, correct? We have all experienced that. Now, analogous to what I just talked about for the X-ray, we want to take away the mechanical scanning property. At the same time, we want to increase the frequency of generation. Now, so now I'm going to introduce to you the MEMS technology. Now, to move away from the piezoelectric way of generating ultrasound, what we are looking at here is to use MEMS technology to make transducer that also have the capability of generating ultrasound. So we have all beat on a drum before. Now, how is a drum made? A drum has a cavity. On this cavity, it has a membrane. So if we vibrate that membrane, it would generate sound, correct? Now, if we were to shrink the size or the diameter of the drum and beat on it, we would generate higher frequency noise. If we shrink it to a level small enough, it would generate sound that we cannot hear in the ultrasound regime. So what we are trying to do is to generate really small drums on the order of microns, the same diameter as the diameter of your hair. So if we can build drums to that dimension and we beat on it, it would generate ultrasound. Now, by using integrated circuit fabrication technique, building such a small drum is actually relatively easy. Now, we also know that if we built a really small drum, the amount of power that comes out of a single drum is really small. But we could build an array of drums. So if we have many drums beating at the same time, then it would be a superposition of the sound power, and we could increase the power that we can extract from this array of drums. So in my lab, we're looking at building arrays of drums to focus the power. Now, that's one reason we want an array of really small drums. The second reason is we want to do scanning applications. Now, I did say that we want to take away the mechanical scanning portion of things and to scan it electronically. Now, if we have an array of transducer, you can imagine each square is generating sound wave. Now, if we beat on this drum with a certain delay, so we would beat on this drum first. This is an activation pulse. We beat on this first. We beat on this second. We beat on this third. And each one of this transducer would generate waveform at different time. And that would mean that all these wavefront would converge at this point at only one single point in time. At all other places, it's destructive waveform. At only this location do all the waveform construct. Now, we could back calculate this. We can then shift this point to somewhere down here. Now, all we have to do is to calculate the distance from this point to all the array and calculate when should we beat the drum. Now, if we can control the delay of activation of these drums, then we could control the focal point of this convergence. Now, if we can actually do that, then we can actually do electronic scanning applications. Now, ultrasound array not only transmit, it also receives signals. So, if we reverse the process that I just talked about, then you could also think of this as I could just listen to a specific point in time. By reversing the delay of receiving the sound wave from a specific point, I could actually only listen to one point in space, and the rest of the noise will be filtered. So we could exploit the phase array focusing in transmission as well as receiving. So in my lab, we have, this is a second engineering challenge that I don't think I'm going to talk about. What we have proposed is a real-time 3D imaging using a roll column imaging technique. I'm not going to talk about this, but I'll just mention this in a nutshell. So if we were to have a 2-degree array, so this is a 2-degree array of ultrasound transducer. This is a 4x4, so we have a total of 16. This is relatively easy. If you imagine that we have 100 by 100, we have a lot of ultrasound to control. So what we are proposing, as opposed to controlling each single element, we control each column. So what we're saying is we would transmit ultrasound by each column and receive ultrasound by each row. So this is what we're proposing in our lab. So we are not firing each individual ultrasound. We're firing from one column, and we're receiving by each row. We simplify the electronic processing of the ultrasound signal. And as it turns out, the quality of imaging for row column is on par with that as addressing each individual element on a 2D array. I'm not going to talk about that, but if you're interested, I can provide you with our publication on this. This is a relatively simple MEMS fabrication technique of realizing the cavity as well as the top membrane, which is the drum membrane, and the top electrode to depress the membrane to generate ultrasound. So we have fabricated all kinds of ultrasound array, 1D array, circular array, 2D array, multiple circular array embedded within each other. All kinds of architecture you can think of, we have fabricated. And we have also integrated the electronics to drive this. This is an example of a 1D array. This 1D array has 32 elements to it. On this 1D array, we have imaged 4 wires. This wire has a diameter of 250 microns. So the transducer is sitting here, and it does a 90-degree sector scan of the 4 wires. You could see that without moving the transducer at all, this transducer is stationary. It has the capability of 2D scan. So we can take away the technician that does the mechanical scanning, we could put the transducer and thus do a 90-degree sector scan. We have also fabricated 2D ultrasound. So 1D ultrasound array gives you 2D imaging. 2D ultrasound array gives you 3D imaging. So a combination of depth scanning as well as left-right scanning, we are able to create 3D images. So this is a spatial distribution of 4 pinheads. Again, the transducer is sitting in the middle, and it does electronic scanning in the X, Y, as well as in the Z direction. We could distinguish the location of 4 pinheads in a 3D space. So this really gives us the ability to do scanning in ultrasound as well as X-ray without moving the probe at all. Now, the second generation of this ultrasound is to integrate the electronics within the transducer. So we have fabricated our own electronics. So by pulsing the CMUTs, or the ultrasound transducer, we want it to be fabricated on a silicon chip, and that could be flip bonded onto a silicon ultrasound transducer. So we could ultimately integrate that within the tip of a catheter. This is another look at our experiment where you have the XY sector scan and the Z scan to create a 3D image that you just saw. The last technology, I'm going to talk about the optical technology. In our lab, we have integrated the optical coherence tomography technology. What's special about this technology is it not only provides the capability of a surface scan, OCT also provides the capability of imaging underneath the tissue. So in this case, this is tissue inside your colon. You could see that the microstructure within this colon tissue is clearly visible. We have fabricated micromirror that has the capability of rotating in XY direction, so it could rotate in this direction as well as this direction. We have fabricated a single mirror or an array of mirror for large area imaging applications. Now, the end goal, again, is to miniaturize scanning mechanism so we can integrate it into the tip of an endoscope, so we could do in vivo biomedical imaging. But at the same time, it's not about miniaturization, it's also about providing better imaging quality. So back in 2003, we have achieved the first 3D MEMS-based OCT image in the world. What you're looking at here is the 3D image of the central nervous system of a fruit fly. So the micromirror is scanning in the XY direction. The OCT is scanning within the tissue. You can see the nerve structure in the center and nerve ending going on both sides. So this cartoon illustrates the central nervous system of the fruit fly. So by integrating the OCT technology onto the micromirror technology, we could create real-time 3D images of tissue and within the surface of a structure. So what we're trying to go with this? Well, the ultimate goal is really to integrate different kinds of imaging modality, be it X-ray, ultrasound, or optical, within a single diagnostic and therapeutic instrument. It could be a catheter, it could be an endoscope, and at the same time integrate a therapeutic X-ray device on here. So what we're looking at in the future is being able to diagnose the extent of cancer by ultrasound, by X-ray, by optical. After distinguishing the extent of the cancerous tissue, we would fire off photon to kill those cancer tissues through this X-ray delivery, in vivo X-ray delivery method. So no longer are we looking at generating photon from outside the body to kill something inside the body. We would do it right on the spot. So this work is not just my work. On the X-ray project, I've been working with David Jeffrey, who's a physicist actually, who works in Princess Margaret Hospital in Toronto. On the OCT project, I've been working with Brian Wilson, again at the University of Toronto, PMH. He's also a physicist who looks at optical imaging applications. Dr. Rob Barnett, who looks at, again, application of X-ray machines, therapeutic X-ray in this case, for radiation therapy applications. And we have been, not listed here, we have been working with Dr. Peter Kim at George Washington University in the States on applying ultrasound to in vivo biomedical imaging. And we have been sponsored by the Gates Foundation, as well Princess Margaret Hospital and St. Kitts Hospital. Thank you.